Okay, there's a video for 2.2 power functions. Your objectives here, I will be able to use power functions to model real-world situations, and I will be able to identify and graph power functions. So let's get into this. A power function looks like this. So what you can see here, A is a power, and then K is the constant. And then x is just our variable. So we say that f of x varies as the eighth power, so if it's like the third power, fourth power, fifth power of x, or that f of x is proportional to the eighth power of x. All right, so if a is positive, we say that f of x varies directly with that power of x. And then if a is negative, we say that f of x varies inversely with the eighth power of x. Okay, so we're going to look at a few functions here and determine if they are power functions or not. Okay, so here we go. We have a constant. We have a variable x being raised to a power. So yes, this is a power function. Okay, how about this one? Well, the way it is presented to us right now does not look like a power function, but I can simplify this because I can take the third power of 8, which would be 2, and then if I want to take the third power, so the third power, sorry, I'm saying power, but I mean to say the third root. So the third root of 8 is 2, and then the third root of 8 to the power of 5. Well, to rewrite this so that it just has an exponent, I can write this as x to the power of 5 over 3. When rewritten in this form, we can see that this is a power function. So this again is yes. Okay, what about this one? So we have a constant, but something different is going on here. Here the x is the exponent. This is not a power function. This is an exponential function. So when the variable is your exponent, this is an exponential function. And then here we go. It's okay for it to be negative. This would just be varying inversely, but this again is a power function. All right, so we're going to do a quick word problem here, so you can see how to use these. So for the gather, guys, another way to gather is you don't have to list everything, but just annotate right there in your paragraph with a highlighter or circle the important parts that you want to focus on when you're coming up with your equation. So we see the volume of a sphere varies directly. That's going to be important because we can, as we saw above, that means we have a positive power. As the cube, well, they're not talking about the shape cube here. They're actually talking about the cube as in the power of 3. So the volume of a sphere varies directly as the cube of the radius r. Okay, when the radius of the sphere, when the radius is 6 centimeters, the volume is this amount. And then it wants to know what is the radius of the sphere, so what sphere, not spear. What is the radius of the sphere whose volume is this amount? Okay, so we've gathered. There's a few different ways you can gather. One is to make a list here. You can annotate your paragraph, but you're just trying to pull out of here what's the important information. So, organize. Well, I know that this is going to be a power function because that's what we're learning here. So, it says the volume varies directly as the cube of the radius r. So it varies directly. Then there's going to be a constant, which we don't know what it is right now, and we know that r is cubed. So this is how the volume relates to the radius when we're talking about spheres. And in here we have the v equals volume. We have r is equaling the radius. And k is just the constant. So how are we going to use this? Well, part of my organize is, how am I going to use this equation? All right, I could plug this in. I could plug in the volume and plug in the radius, but that's not going to give me the radius when I have a different volume. So how I'm going to use this equation is I'm actually going to plug in my first volume and radius, find out what the constant is in this situation, and then use that to find out what the radius is going to be with a new volume. Okay, so part of organizing is to come up with a plan, and I did come up with this plan, and you should write this down because this is how we're going to use power functions when we're modeling. You have to actually use the formula to find k, and then use k with a different volume to find the radius. So each time you're going to have to find k first. Okay, so I have my volume. And now I'm going to solve for k. So I end up with k equals, and I'm not going to round this until the very end. So I'm going to take this whole thing, 904,779, and I'm going to put it over. I can simplify 6 cubed, which would be 216. But rather than actually dividing this and rounding off or writing down every single number my calculator gives me, I'm just going to leave this just as this. And then I'm going to put it in my new equation and set it all up so I can just type it into my calculator as one big thing and round at the end. All right, so now I have a new volume. The new volume is 268.083. And my k is right here, so 904.779 all over 216 times radius cubed. All right, I need to solve this for my radius. So I'm going to multiply by the reciprocal. So I'm going to take this, multiply both sides by the reciprocal, and then I'm going to take the cubed root of that. Okay, so I multiplied 216 times 268.083. I divided, I got this number, I divided by this, put it right there, and then take the cubed root of it. I punch all this into my calculator, and I get R equals 4.000016, so I'm going to go with 4. And actually, let's change this so it says approximately 4. All right, so learn, what did we find out here? The radius of a sphere whose volume is 268.083 is approximately 4 centimeters. I don't know why I spelled whose that way. I will fix that. Okay, there we go. Let's move on to how to graph these. All right, so what I've done is I've broken it down basically into 3 steps for determining how to graph these. I could show you every possible situation of odd over even, even over odd, that kind of thing, but I think it's easier to think of it this way. So the first thing we're going to learn or plot or graph when we do this is whatever's happening in quadrant 1. So there's 3 different situations here, and they each have a different look in quadrant 1. So if I have an exponent, if I have a power function whose exponent is between 0 and 1, like f of x equals x, let's say 1/2, well, this is the same as the square root of x, which I know you guys know what that looks like. Just looks like this. Okay, so we're only concerned with what's happening in quadrant 1, but if we were to have, let's say, x to the power of 2/3, same deal. If it's between 0 and 1, it's still going to look like this. Okay, just for this part. Okay, we're not done graphing. I'm just telling you what it's going to look like on the right side. Okay, if the exponent is more than 1, so one that we are familiar with, very familiar with, is x squared. We know that the right side of the graph for x squared looks like this. Same deal, even if we have a fraction, and we'll get into how to graph the rest of this function a little bit. But let's say I have 5/2. Okay, it's still going to look the same on this side. All right, less than 1. So now we're talking about negative exponents. So x to the power of -1, well, this is the same as 1 over x, the inverse function. Right? We also talked about it varying inversely, so that should make sense for you. Okay, this looks like this. So anytime that power is negative, this is the shape we're going to get. Even if it's a fraction greater than 1, a fraction less than 1, That does not matter. If the power is negative, the right side of the graph is going to look like this little swoopy thing, where we have a Hasse and a Vassy. Okay, what happens if the k, the constant, is negative? Well, flip over the x-axis if the k constant is negative. So let me give you an example of this. If I were to have negative, well, actually, write f of x equals negative x to the 2/3. We're still only concerning ourselves with the right-hand side of the graph, but now this is a number less than 1 but greater than 0, so it's going to go like this, but it's going to be flipped over our x-axis here. We have f of x equals negative x to the power of 3/2. Well, this is a number that's greater than 1, so it would go like this, except that we want to flip it over the x-axis here, so it's going to go like that. And then lastly, if we have a negative constant and a negative exponent, well, typically it would do swoop here. Instead, it's going to do swoop down here. All right, so let's pull it all together with the last thing here. So determine left side of the graph by plugging in -1 for x and calculating if the y value would be positive or negative. Okay, that's going to tell us, because if we have, well, let me just give you an example here. Let's try f of x equals x to the negative 2/3. Well, what is this saying here? Well, this is saying 1 over, and then let's actually change this into the radical that it is, 3 x squared. Okay, so if I were to plug in a -1, so if I do f of -1 and plug it in here, well, when I square my -1, that's going to give me a +1. And then when I take the cubed root of +1, that's going to give me a +1. And then +1 divided by +1 is 1. So let's graph this whole function here. So we have a exponent that is negative. So we already know that it's going to be a swoop. We want to check to see if there's a negative out front here. There's not. So that means the right side of our graph is going to be right here. And then the left side of our graph, when we plug in -1, we plug in this x, well, we get a +1 out of it. So the left side of our graph is going to be in quadrant 2. When I plug in a negative x, I get positive y's. So there we go. If negative, graph is odd, so reflect over the y-axis and the x-axis. So let's see what that looks like in an example here. If I have x to the 3/5, okay, this is the same as the 5th root of x to the 3rd power. I'm now going to do f of -1, plug it in to see what's going to happen here. So -1 cubed, well, -1 times -1 times -1 is -1. And then the 5th root of -1 is -1. Okay, so now let's graph this whole function here. The right side, well, this is a number between 0 and 1. So the right side's just going to go like this. I don't need to flip it because there's not a negative out here. So I'm just going to go like that. And so when I plug in -1, when I plug in this x, I get out a -1. So I get out a point right there. So what that means is I'm going to reflect this over the y and then over the x. Just like that. Okay, if undefined, there is no left side. So you hopefully are seeing where this is going, but we're going to create an equation, or I'm going to give you an equation, where we can't take the even root of a negative. So let's try x to the power of 7/4. So this is the same as the 4th root of x to the power of 7 I'm going to plug in -1, and I have the fourth root of -1 to the 7th power. -1 to the 7th power is -1, so I have the fourth root of -1. But this, I can't actually figure out what this is. This is going to be, well, it would be a imaginary number, right? So this is actually an imaginary number. So what does this look like on the right-hand side? Well, this is a number that's greater than 1. It is not being flipped over the x-axis, so it goes like this. And then since this would just be an imaginary number, where you can't graph imaginary numbers, we're done. There's nothing to graph on the left side of our graph here. And you know what? I'm going to change this in your notes. I don't want to call this undefined. I'm going to call it if imaginary. Okay, so I've given you something for you to try down here. You're going to match each function with its graph. You can use a letter more than once. So if I have x to the power of 4, I don't really care what this 2/3 is doing. That's just going to be a stretch or shrink. I really just want to know generally what the shape is. So power of 4 means it's going to go up like this, but now it looks like I am flipping it. So it looks like it's going to be this one right here. So the first one here is I. All right, you try the rest and we will go over them in class. Thanks for watching.